right. We are discussing periodic classification and people who are preparing for their pre-engineering tests and pre-medical tests. Well, listen to me carefully because after finishing any of the subtopic in this particular topic, we will be linking that to what? Your exam. Other than that, we don't discuss anything. So if you wanted to learn the subject intense, you are welcome. You can actually listen to the lecture. If you wanted to link that to your exam, that also will be followed by the discussion, right? And in the process, well, I would love to remind everyone who are actually dealing with periodic classification. Remember that you have 120 odd elements in the periodic table. Every time I remind this to you. And you're not asked to place them in an order just like that without any basis. Remember that there are schemes, there are principles, there are rules in which you have placed these elements in rows and columns. You must understand, the rows being periods, the columns being groups, and we are exclusively dealing with long form of periodic table proposed by Moseley, where you have 7 periods and 18 groups. And what is very strange here is, the 7th group itself is incomplete. That leaves the scope for you, it's an open scope even for you to do some research on it, right? The 7th period itself is incomplete. And everyone must understand that each period is supposed to be a shell that's nothing but the principal quantum number proposed by Bohr. And in an atom, you have infinite number of shells, so you must be having infinite number of what? Periods. It's as simple as that. And when you have infinite number of periods, then 7th period itself is incomplete. Then it gives you a large scope for you to go out, venture out and see if you can discover some elements. And for you, I'm waiting for you to put this element in a proper position in the periodic table. And also its properties are very much known to you, which stimulates what? Research, right? In that process, when you arrange all these based on some rules and principles, you always have some properties which repeat itself at regular intervals, right? So the properties that repeat itself at regular intervals can be called as what? Periodic properties. And the most fundamental thing I was always telling you, and I wanted to remind you every time, is basically understand, even though you have 120 odd elements in the periodic table, and the basic difference between the mode of activities. When I say mode of activities of this particular element, I'm referring to their chemical properties and physical properties which they exhibit. So the basic difference, why they exhibit certain mode of activity is basically nothing but atomic radii or the size of the element. You must understand. So if the size of the element is varying, accordingly, the periodic properties or the mode of activity shall be varying. So based on this, the periodic law has been framed. That's why people say the chemical and physical properties of an element is basically a function of what? Atomic radii. So even though you are actually proposing different periodic properties, and when I frame a function, ultimately it boils down to what? Atomic radii. You must understand that. Right? So what is happening here is I was actually telling you, I was defining the basic thing that is atomic radii. We had some difficulties, so I was proposing some operational definitions for you depending on the nature of bonding that is present, because you have operational definitions being atomic radius, operational definitions being covalent radius, van der Waals radius, ionic radius, and what? Metallic radius. So you have all the 4 for you. So understand that, right? And the second periodic property which repeats at regular intervals, I was telling electropositivity. And electropositivity, as you know, is, it's told for what? Metals. Because the ease or the tendency to lose electrons is we only see in what? We only see in what? Metals. So metals are basically electron vomiters, you must understand. The second, the details have been given to you. I'm just briefing so that I can move ahead. And the second one which we were discussing is electronegativity. Electronegativity. And understand that electronegativity is a term which is basically used for non-metals. And non-metals, the tendency to attract an electron pair towards itself. That means that electron lovers are basically non-metals, electron vomiters are basically what? Metals. Well, whether it's electropositivity or electronegativity, these are nothing but tendencies. And if they are tendencies, they don't have any units. If you want to assign some arbitrary numbers to them, they just signify the magnitude in which, just checking with the number, you can actually say how great electropositivity the element possesses, or how great electronegativity an element will be possessing. This is what is conveyed by an arbitrary number, but otherwise the tendencies of vomiting electrons or loving electrons, I think they do not have any units. And also I was telling about electron affinity, right? Electron affinity again is a periodic property which is told for what? Non-metals. Right, so non-metals. So what happens in electron affinity is it is exclusively exothermic. It's exclusively exothermic. So what you do is you take an electron and add it to a neutral gaseous atom. When you add it, suppose if it is catching the electron very tightly, that means it's exhibiting great love, right? Great lateral love. The electron is holding the electron which you're dropping very tightly. The more tighter it is, the greater is the energy released. So electron affinity is basically what? Exothermic reaction, and this tendency of attracting electrons and holding it tightly releases energy, and that energy is referred to be what? Electron affinity. You must understand. The first electron affinity is always negative, that is exothermic reaction. The second electron affinity onwards, I think it's an endothermic reactions because repulsion start, right? If this is the case, then let us actually link this with what? Oxidizing power with basically electron affinity. This is what is our discussion. Mind you, if I say electron affinity being love for electrons, well, if I'm able to pull the electrons from my neighbor, if I'm able to pull electrons from my neighboring atom or a substance, then I think the substance, your neighboring substance, gets oxidized. And who has done that? I have done that. So I become an oxidizing what? Agent. So what happens is, if I can frame a function to you, then I think you can say oxidizing power is basically a function of electron affinity. The more the love you exhibit, the more the energy it is released, then such elements have said to be possessing greater oxidizing power. This is what, it's a common sense, right? Because when someone is pulling electrons from you, you get oxidized, and the fellow is attracting the electrons towards itself gets reduced. And that's how the oxidizing power is defined, and it's a common sense, right? If this is the case, if I can give you the exact relation, then oxidizing power and electron affinity are directly related. Greater the affinity for electrons, greater is what? Oxidizing power. That's what it means. If this is the case, then understand that electron affinity of chlorine is greater than electron affinity of fluorine. And I was telling you very detailedly, well, remember that even fluorine and chlorine both belongs to the 7th group, and that's nothing but the halogen group. And they are placed to the extreme right top in the periodic table. They are placed to the extreme right top in the periodic table. So both are non-metals. So in fact, both are great non-metals rather. If they are both great non-metals, then I think the love for electron would be of the same magnitude. Except for fluorine being small, there will be no space for the extra electron which you are adding. So there might be slight repulsions between them. So the electron affinity value falls just below what? Chlorine. This is what our discussion is. But anyway, the final conclusion is basically electron affinity of chlorine is greater than electron affinity of chlorine. That is the truth. In fact, I would like to say chlorine possesses the highest electron affinity in the periodic table or in chemistry. So there is a sweeping statement, you can't change this. The electron affinity of chlorine being greater than electron affinity of fluorine. So the expected trend, I can write it here. the expected trend of oxidizing power would be, then it implies the oxidizing power of chlorine is greater than the oxidizing power of fluorine. You can understand that. So it's a follow-up thing, because greater the electron affinity, greater is what? The oxidizing power. So basically you can see the oxidizing power of chlorine is greater than what? Oxidizing power of fluorine. And because this is what we are telling, right? And this should be the expected trend. But in practice, actually, the real trend, if you actually see the real trend, then you can actually see the trend having a discrepancy. Oxidizing power of fluorine is rather very much greater than what? The oxidizing power of chlorine. You must understand that. That is the real trend. When such discrepancies occur, when we were very confident while uttering such statements in the beginning, that oxidizing power must be a function of electron affinity, then understand that, the guy who is actually loving electrons must be possessing greater oxidizing power. That statement is of course correct. This is correct, what we have done. This is also correct. This is also correct. But the expected trend must be this. But I think this is correct and this seems to be wrong. Then understand that just because there is a discrepancy, the initial things are not wrong. The common sense is suggesting when you expect something and it goes out as a discrepancy, then the only thing that must strike in your brain is basically that there are several other factors which are basically influencing what? The oxidizing power, and oxidizing power not alone depends on what? Electron affinity. That might be the reason, but otherwise there is no point for what? Discrepancy, you must understand. But what is important in exam? Yes, the important thing in exam is, even though the question will be like this, even though electron affinity of chlorine is greater than what? Electron affinity of fluorine, but still I think the oxidizing power of fluorine is almost very much greater compared to what? Oxidizing power of chlorine, and we need to answer that. And during the process of answering, you have several questions which will be coming in the exam, right? So what is that? Let us understand this. First of all, what we will do is we'll justify some reactions that fluorine is a better oxidizing agent compared to what? Chlorine, right? So why there is a discrepancy? Already you think in rational terms. It is not alone the factor. Electron affinity is not alone the factor. It's basically not alone the factor which will determine what? The oxidizing power. There are several other factors which determine what? The oxidizing power. You must understand that. Hence you have a discrepancy. Now what is the other factors which will determine? Let me check it out first, then we'll give justification and then we'll go for the trend, right? So let us actually see why such a thing would happen. Watch carefully here. I'm giving you the explanation for this, right? So basically, this is the question. Electron affinity of chlorine is greater than electron affinity of fluorine, but still oxidizing power of fluorine seem to be greater than the oxidizing power of chlorine. I have put greater. That means its oxidizing power is very much greater than what? Chlorine, even though chlorine possesses more love for what? Electrons. We need to answer that. How do you answer this? First of all, what you do is you just recollect. I draw the attention of everyone, please. I draw the attention of everyone. Just recollect what is the definition of electron affinity. I'll write it for you. In fact, the definition of electron affinity is energy released when the electron is basically added to a neutral gaseous, and I highlight this, atom. So recollect electron affinity definition. You just recollect the electron affinity definition. What is it? It's nothing but energy released when an electron is added to a neutral gaseous atom. I would like to underline this atom n number of times for you. Must understand. It's about adding electron to an atom. It's to an atom, neutral, isolated, gaseous atom. When you add the electron, if the added electron is held tightly by the nucleus, then the energy is released, and that released energy is nothing but what? Electron affinity. This is what we were told about electron affinity. Right? If you can recollect that, then come here. Come here. Then you say that the electron affinity of chlorine is greater than fluorine, but still oxidizing power of fluorine is very much greater than this. And if you can write the reason for that, yes, the reason is, first of all, you do not find atoms of neither fluorine nor chlorine. You don't find, right, fluorine atoms or chlorine atoms. If you would have found out the fluorine and chlorine atoms, then I think you can straight away, apply the definition of what electron affinity you must understand, right? So we don't have atoms. So fluorine is such reactive element. Halogens are so reactive, they combine with each other through a covalent bond, and they exist as diatomic molecules. So rather, you do not find atoms of fluorine and chlorine, but rather fluorine, chlorine, they exist as molecules. You must understand. They exist as what? Molecules. So now what happens is, your primary duty is, first of all, convert the molecules to what? Atoms, and then try to add an electron, then it will catch it, and then the electron affinity comes in. But primarily, you must first what? Convert these molecules to what? Atoms. Well, here comes an extremely important question, and I'm telling you, you can basically bank on this question. This question is for sure in exam. This question is absolutely sure in exam. I'm telling you, this is for 4 marks for your JEE or NEET. This question will be asked in exam which I'm about to write. Please bank on this question. You will get this question for sure, right? What is the question? Watch carefully here. So, the sequence is like this. The sequence is, first the fluorine molecule, this is the molecule, first need to get converted to fluorine atoms. And then you add an electron, then it catches the electron and the electron affinity is released, which is exothermic reaction. So the first thing what you're supposed to do is, you take a fluorine molecule, break it into atoms, and then try to add an electron. You're not adding electrons to what? Molecules, because the definition says the electron is added to neutral gaseous atoms. It's not molecules, and halogens don't exist as what? Atoms. They will be existing as molecules. Same is the case with even chlorine. So what you're supposed to take is this chlorine molecule, right? Then you break it into atoms and then add electron, then the Cl minus, and then the electron affinity, and this is exothermic. So that is how it is. If that is the case, now everything has been stopped here. Now the question is, the one which can break easily, the bond which can break easily, that readily forms the atoms. If that readily forms the atoms, then I am in a position to take that atom and add an electron, and the electron affinity is released. Right? That makes you a very good what? Oxidizing agent. So here 2 things are actually applicable. Remember, so what I mean is basically, oxidizing power now is a function of, no doubt, electron affinity, but at the same time, even oxidizing power is even function of bond dissociation energy also. So remember, oxidizing power is now a function of electron affinity, and even oxidizing power is a function of bond dissociation energies. Because you don't have atoms, you have to break that molecule to what? Atoms, then add an electron. That is how it is proceeding. So remember, this is what it is. Then if you see, oxidizing power in fact, is directly proportional to electron affinity. It's correct. But now the newer one, oxidizing power, is inversely related to the bond dissociation energy. Lower the bond dissociation energy, more is what? Oxidizing power. And remember, I was telling you very clearly, for fluorine and chlorine, there is not much to distinguish in electron affinity. I can simply say both are non-metals, both are great lovers for electrons, except for fluorine drops below chlorine for few units, 2-3 units. But otherwise, both have same values of what? Electron affinity. So there is not much to choose between the electron affinity values of what? Fluorine and chlorine, because they are almost equal. Now everything now boils down to what? Bond dissociation energy, which is inversely related. Smaller the bond dissociation energy, then I think it will be easy for you to have atoms, and the atoms will take the electrons, and taking electrons you can't much distinguish between fluorine and chlorine because both have similar values. So now the thing is, choose the fellow who has lower bond dissociation energy. And I was telling you, a trend which I will be writing now, that trend is 100% sure in exam. You can bank on it. It is 100% sure in exam whether you are writing a pre-engineering test or a pre-medical test. This question will be asked, right? Let me write the trend. Now what are we doing? We now need to choose a bond dissociation energy between fluorine and chlorine and see that who is least. That will determine the oxidizing power. It's as simple as that, right? And if I can write the trend of bond dissociation energies in halogens, if I can write the trend of bond dissociation energy in halogens, well, it all starts from chlorine greater than bromine, and then comes fluorine. Well, remember, the fluorine is kicked to the third position in halogens. In fact, approximately, if I can write it, if this is 58 kilocalories, the fluorine is just 26 kilocalories. It's half of that. So it's very easy to break what? Fluorine molecules. It's very easy to break fluorine molecules and then go for electron affinity, right? So what happens is, now the fluorine has almost half of it. So you can see these fluorine atoms, you can break it with 26 kilocalories and you have fluorine atoms, and if you add an electron, they will catch it and the electron affinity is done. But the chlorine struggles. This is 58. So it's basically struggling to get what? Chlorine atoms. Then if you add an electron, it forms Cl- and it gets E2. But the difference between E1 and E2 in the form of electron affinity is not much, except few points here and there. But otherwise, the basic thing which will determine the oxidizing power is basically nothing but the bond dissociation energy and nothing else. You must understand, right? So what is the gist of what I'm telling? Where do we start with? I think you understand that this is electron affinity of chlorine is greater than what? Fluorine. In fact, electron affinity of chlorine is highest in chemistry, right? So if the electron affinity is greater, then actual trend is oxidizing power of fluorine is greater than chlorine. It actually should be reversed. But the trend got reversed here. And for that, the explanation has been being given for you. So if that is the case, then the issue is you don't find what? Fluorine and chlorine atoms. You need to break them. Because electron affinity definition says you need to add electrons to neutral gaseous atoms, not molecules. And you don't find what? Fluorine and chlorine atoms at all, because they are diatomic. And they're extremely reactive. They are not monoatomic at all. They are all diatomic molecules. So the first thing what you're supposed to do is convert them into what? Atoms. And converting them into atoms depends on the bond dissociation energy. So I said oxidizing power, no doubt, is depending upon electron affinity. There is not much to choose between the electron affinity values of fluorine and chlorine, because both have almost similar values. If that is the case, then it boils down to the second factor. That's nothing but the bond dissociation energy. It boils down to the second factor, that is the bond dissociation energy. And I am telling you that there is a trend which is always asked in exam, and I would like to highlight this. In fact, the trend of bond dissociation energies, this will be asked in the exam for halogens. And if you see, the bond dissociation energies for chlorine is highest rather. It is highest and not for what? Fluorine. So fluorine is basically kicked to the third position, and it all starts from chlorine. So if that is the case, then I think fluorine is easily forming atoms because it's half the bond dissociation energy of chlorine. It readily forms what? Atoms. Then you are able to add an electron. So you must understand that, right? If this is the case, then simply speaking, how do you write it in the form of a statement? Two things which are important, right? Well, I would like to explain this. Watch carefully here. So the conclusion is basically, like this. The conclusive part is basically, what I mean is, electron affinity of chlorine is greater than electron affinity of fluorine. This is true. Also remember, bond dissociation energy of fluorine is very much lesser compared to bond dissociation energy of chlorine. Also remember, oxidizing power is directly proportional to electron affinity, and oxidizing power is inversely related to the bond dissociation energy, right? And in this case, electron affinity of fluorine is almost equal to electron affinity of chlorine. So there is absolutely nothing to choose in electron affinity values. So ultimately it depends upon the bond dissociation energy. So that's why, since fluorine has least bond dissociation energy, that's why fluorine is a powerful oxidizing agent than chlorine. We would like to justify, we would like to definitely justify fluorine is a better oxidizing agent. You must understand that. We will do that. But ultimately it's all about what? Bond dissociation energy. Which of the following is true? Then I think the bond dissociation energy of fluorine being the least, making it a powerful oxidizing agent for the assertion reasoning questions, or which of the following true is one type of question. You must understand. At the same time, remember the trend also. That is, this is the trend where fluorine is almost half the value of chlorine. You must understand. Well, we wanted to know why the bond dissociation energy of fluorine is even smaller compared to chlorine, even though they belong to the same group. We wanted to answer that. If you wanted to answer that, then let me put it as a supplementary question to you, such that we get the knowledge of that also, rather than writing a simple dry trend. Let me even explain why fluorine has the least bond dissociation energy, which is making it a powerful oxidizing agent. If that is the case, let me explain that also for you. Let me see, right, can you explain this trend? The trend of bond dissociation energies, in halogens are basically, this is how it is: chlorine greater than bromine greater than fluorine. Why such a thing? Why this trend? Why this trend? Let us explain that. Why such a trend is happening? Well, we would like to write this, because look into this. If I can write the fluorine atom, and let us actually post-mortem its covalent bond. That is fluorine. It has a single bond between two fluorine atoms. And fluorine belongs to 7th group. It belongs to 7th group. Out of this 7, it belongs to 7th group, means the total number of electrons in the outermost shell are 7. And there is significance of outermost shell because it is only outermost shell which participate in bonding, are readily available for bonding. That way we can say, if you have 7 electrons, 1 you invested in this. So when you invest 1 in this, then you are left over with 6 electrons. So here is 1 pair, here is 1 pair, here is 1 pair. So total, if I account for the total number of electrons in fluorine, this is 2, 2, 2, which is 6. And the one which you invested in this bond is 7. Same is the case with even this fluorine. If I can write it, 2, 2, and 2, right? One you invested here. So this bond is having 2 electrons and this you have 6. So this is 3 pairs of electrons which are called lone pairs. Lone pairs. Now what are lone pairs? A pair that belonging to valency shell and doesn't participate in bonding, but otherwise it is readily available for what? Bonding. A pair that belongs to valency shell. Not every pair is a lone pair. A pair that belongs to valency shell but doesn't participate in bonding but readily available for what? Bonding can be called as what? A lone pair. And each fluorine atom is having 3 lone pairs. You can see here 1, 2, 3, 1, 2, 3 and 1 it has invested. Same is the case with even chlorine. If I can write chlorine for you, since it belongs to the same group, you can see here it has invested 1. It has invested 1 and same is the case with chlorine also. You have 3 lone pairs. Now the issue is the fluorine atom is so small. The fluorine atom is so small. In fact, it is the smallest in periodic table, I can say. How do you say that? Because the size decreases from left to right. The size decreasing from left to what? Right. If the size decreases from left to right, then understand that you are starting from the first group, you walk to the 17th group. 17th group top element is fluorine. 17th group top element is fluorine means from left to right the size is going on decreasing and the smallest elements are placed to the extreme right top. Forget about noble gases. Noble gases belong to what? The 18th group, but 17th group must be considered and the fluorine is the smallest atom. If the fluorine is smallest, then what happens is this being the smallest atom, what happens is the bond length is very small. They go very close to one another. Then since it is small, the bond length is very small. The bond length is too small. The bond length is too small means the fluorine atoms have gone very close to one another and stopped at a distance. The fluorine atoms being smallest, they have gone very close to one another and stopped at a distance. If that is the case, then what happens? Since you have the bond length being very small, that leads to what is, since it is very small bond length distance, this lone pair and this lone pair, this lone pair, this lone pair, this lone pair and this lone pair, they generate repulsions. They generate repulsions, you must understand. And that I call it to be interelectronic repulsions. Remember, electron is a cloud and the lone pairs enjoy freedom because they belong to one atom. Bond pair belongs to 2 atoms, whereas lone pair belongs to only a single atom. When it belongs to a single atom, it is enjoying freedom. It enjoys freedom. And you can see here 3 lone pairs on fluorine, and the fluorine has gone too close to one another. And I think these lone pairs are utilizing their freedom. They are utilizing their freedom and the clouds are moving towards one another, generating interelectronic repulsions. When they repel, these repulsions will have a bearing on the bond length. So that's the reason why this fluorine actually breaks easily. This breaks easily compared to chlorine. Chlorine atom also has 3 lone pairs. But the bond length of chlorine is bigger than what? Fluorine. Because down the group the size increases. And chlorine is below fluorine, you must understand. Since it is bigger, the bond length is bigger. The interelectronic repulsions the effect will be very less because you are far away. So the bond length is bigger and you don't find interelectronic repulsions. Of course you will have it, not of that magnitude of fluorine. You don't break easily the way the fluorine breaks. That's why the bond energy of chlorine is 58.5 kilocalories and approximately, and the fluorine comes to half of it, almost 26 kilocalories, you must understand. And that is because of interelectronic repulsions, you must understand this, right? If I can put it properly to you, let me put it properly, right? What is that we are discussing and why such a thing should happen, right? And look into this. Look into this. If you look into the trend of bond dissociation, the trend of bond dissociation energies, then it is chlorine which is highest compared to bromine compared to fluorine. And the reason for that, if you actually reason for that, the reason which I can quote, I call this to be inter-electronic repulsions in fluorine, and that's due to small size of what? Fluorine. You must understand, small size of fluorine, because it's placed to the extreme right top in the periodic table. Right? Then, if that is the case, how do you explain this? Then I think you can write it here. This is fluorine. This is small. This is small. And the bond length will be also what? Small. And you can see here 3 lone pairs. They repel with, they generate what? Repulsions. And when they generate repulsions, the fluorine bond breaks easily. And 2 fluorine atoms. And the bond dissociation energy is 26 kilocalories. If the case of chlorine, its bond length is large, is bigger bond length, right? And you can see here, these are the lone pairs. No interelectronic repulsions. Not much, rather. I can't say no. Not much interelectronic repulsions. And then the chlorine breaks into 2 chlorine atoms with an expense of 58 kilocalories. So bond length is more. Bond length is more. So ultimately the effect of this is falling on oxidizing power. Oxidizing power is inversely related to bond dissociation energy, and the bond dissociation energy of fluorine is lesser than chlorine. So oxidizing power of fluorine is greater than what? Oxidizing power of chlorine. You must understand that is how we explain, and you have questions in this, you must understand this, right? Now comes, let us justify why fluorine is let us justify that fluorine is what? A very good oxidizing agent. Let us justify this. Watch carefully. Let's give justification for this. Observe carefully. What I'm trying to do is, justification. Justification for fluorine, better oxidizing agent than chlorine. Well, one reaction says all. You have n number of reactions. I take one of the reactions and you can see how both behave, right? And in fact, let us take the case of fluorine plus hydrocarbons, right? It will justify everything. If you look into fluorine plus any hydrocarbon, in fact any hydrocarbon, the reaction is so spontaneous that you are left with carbon and HF. You must understand. And this carbon got oxidized. It got oxidized because the losing of hydrogen is oxidation. Loss of hydrogen is what? Oxidation. And the reaction is so vigorous. The reaction is absolutely vigorous. It's vigorous and you got what? Carbon And this is a fluorine oxidizes methane to carbon. And the reaction is absolutely vigorous and what? Spontaneous. Whereas if you take chlorine, it struggles to give the same. First it gives something like this. Then it gives this. Then it gives your chloroform. Then it gives carbon tetrachloride. That too in presence of sunlight. You require someone to help you out. Sunlight, ultraviolet light, or some light using as a catalyst. It is a photochemical reaction, free radical mechanism. And then it is not vigorous as what? Fluorine, you must understand it. Right? So it's not so vigorous. So this equation is justifying, this is a great justification, thus fluorine is a better oxidizing agent compared to fluorine. The reason being the bond dissociation energy of fluorine is smaller than chlorine. You must understand. Right. Now what we will do is we'll proceed ahead with the next periodic property, which is extremely important, where many of the applications do come in. But remember the scheme in which we are presenting the periodic properties. What we do is first define the periodic property. First define it. What exactly is it? And then we'll frame a function. Function means on what factors does it depend. That is the second one. And the third thing what we are doing is once the function is framed, we would like to know the trend in which it is varying in the periodic table. Because after all, periodic properties are properties that repeat itself at regular intervals in the periodic table. So we need to tell the trend also after defining the periodic property. And then we'll go for the applications. And the application part is, of course, the questions in exam you must understand. So I proceed ahead with the other periodic property. That's nothing but the ionization potential. Ionization potential. Or I can simply say, I call this to be ionization energy. It's ionization energy also. Right? Let us define. The sequence is first we define, then we frame a function, and then we'll get into the trend, how it varies in periods and groups. And the fourth one is application. Where do we use it? And what are the questions in the exam? Right? We don't discuss anything without linking any subtopic with what? Exam. After all, that's important. Right? So ionization potential, let's define it. Right? Well, I would like to define ionization potential for you. Definition. Look into this. Wherever required, I am underlining. I do underline that because that will give you a hint of on what factors that ionization potential depend upon. So I would like to highlight it, right? So if I can define this, well, this is energy required. It's basically energy required, right? Energy required. So when I say energy required, it's exactly opposite to electron affinity. Electron affinity is energy released. It's exothermic. Here it is required, and it's a common sense because electrons are bound to the nucleus with certain energy. They are bound to the nucleus with certain energy. And if you want to extricate it, the same amount of energy you need to spend it out to kick the electron out from the orbit. So it's as simple as that. So energy required to extricate an electron, energy required to extricate an electron from the outermost shell of a neutral gaseous atom. You must understand. So it's basically energy required. So it's basically endothermic reaction, you must understand. And it's required to extricate. Extricate, the English meaning of this, the extrication is nothing but energy required to remove an electron. You need to remove an electron. For removal of electron, you must be spending energy because the electron is bound to the nucleus with certain energy. Remember why I call this potential? Why I call this potential? Because I have done work. I have done work. I have done work in bringing the electron from infinity to a certain point where the point is under the influence of the nucleus. So I have done work. So if anyone wanted to extricate the electron from the influence of the nucleus, then after all, the same amount of work which I have spent, you need to spend to extricate it. It is as simple as that. Hence, it is called potential, because potential is nothing but the work done in physics terminology. So you must understand this. It's ionization potential, right? So energy required to extricate an electron from the outermost shell of an atom. In chemistry, the outermost shell has significance. Not every electron will participate in atom. Mind you that you can strip the atom naked also. That's not the issue. Remember that. Even though we speak of outermost electrons, because that's significant in chemistry, you can strip the atom naked. And the naked atom is basically nothing but the fourth state of matter. That's nothing but what? Plasma. Plasma is a naked atom. But that can be done at what? Extreme temperatures. Extreme temperatures in fusion. So those are not normal conditions. So normally in chemistry, it is the outermost electron which participates in what? Electrons. So the outermost shell assumes significance. But at the same time, yes, you can strip the atom naked. Yes, you can strip it. Right? But that occurs at what? Very, very high temperatures. You must understand. So energy required to extricate an electron from the outermost shell of a neutral gaseous atom. Now, if I can have a closer look of this definition, what is he basically telling is this. Watch carefully here. You take a metal M, right? This is a solid. That is a solid, right? He wanted to first convert this metal solid to a neutral gaseous atom, right? Then from that you are supposed to remove an electron. Remember, you are removing the electron from what? A neutral gaseous atom. It's not the other way around. So what you do is he's asking us to take a metal M, because remember, ionization potential is a term which is used for what? Metals. Removal of electrons must be attempted only for metals. It is ridiculous that someone is telling you that I have removed electrons from fluorine, chlorine and all. You can slap him. You can slap him comfortably. Because you removing electrons from what? Non-metals is ridiculous, because they are electron lovers. Don't even attempt that. No one has removed electron from what? Fluorine till date. It is only fluorine which will remove electrons from the others, making it a powerful what? Oxidizing agent. So again, I am telling you the ionization potential, what we are discussing now as a periodic property, is basically told for metals. So we are attempting to remove an electron from a metal atom which is converted to a neutral gaseous atom. You must understand. So here is a metal solid. First, you need to convert this into a gas. Convert that into a gas. When you convert that into a gas, this is what is called neutral gaseous atom. You must understand. That's called the neutral gaseous atom. Now recollect that a solid converting to gas won't happen with magic. You're not doing like this and it converts what? The solid converting to gas. And remember, you have missed it in between one state of matter, that is liquid state. So what you're doing is the solid straight away getting converted to what? Gas. You must understand. It's converted to gas, right? And the process of conversion of the solid to gas directly is sublimation energy. It's sublimation energy. The process of conversion of a solid straight away to gas can be called as what? Sublimation. So he is requiring first you convert the metal solid to a gaseous atom first. You do that first. Then he is telling us, take the metallic gaseous atom, this is the neutral gaseous atom, and then try to remove the electron. Then this is the extrication which he is speaking of. And this is energy required. So it's basically endothermic, and this is what is called ionization, that is the first ionization potential, or I call this to be I1. You must understand, that is the first ionization potential. So have a clear idea of what you're doing. You cannot be just casual in dealing with definitions, right? So what is ionization potential energy required to extricate an electron from the outermost shell of a neutral gaseous atom? Now, how do you get a neutral gaseous atom? Is basically convert that into what? Convert that into what? A gas straight away, and the process is called what? Sublimation, right? And then from that you remove an electron. For that energy is required, and that is called the first ionization potential. That is the first ionization potential. You must understand this, right? If this is the case, then understand it's a common sense. I have some applications for you, application number 1, application number 2, and let us see what they are. And I wanted to link this, and first of all, frame a function. First of all, frame a function, right? Let's frame a function for this, right? Observe carefully. Observe carefully. Observe carefully here. Now, ionization potential depends on what? Depends on what? It depends on what? It depends on what? I think it is simply, I can say that ionization potential again is a function of what? Size. Because you're trying to remove an electron from the outermost shell. The greater the distance between the outermost shell and the nucleus, it's easy for you to remove the electron. Easy in the sense, the energy required to remove such electrons would be easier for you. Would be easier for you. You must understand this. If this is the case, ionization potential is function of size. If you look into the exact relation, IP is inversely related to size. In fact, greater the size, less is ionization potential. So, I can simply say alkali metals have the biggest sizes, so have least what? Ionization potentials. You must understand. Because left to right size decreases, and alkali metals are placed to the extreme left in the periodic table, and I think they have the least ionization potentials. You must understand. And if you look into this, if you look into the trend, in period, the size decreases, so ionization potential increases, right? In groups, the size increases, so ionization potential will actually eventually what? Decrease, right? That is a trend. So ultimately you look into this, what is significant here, you give any periodic property to me, ultimately it's a function of size. That's why I said, and I keep on reminding you, that you have many elements in the periodic table, and the mode of activity of that particular element, the mode of activity I'm referring to, the physical and chemical properties of that particular element is ultimately a function of size and nothing more. Lithium would be lithium because of its small size. Potassium will be potassium because of its small size, and iron will be iron because of its size. Remember that it's all about size. That's why while discussing periodic properties also, we discussed first the atomic size, that is atomic radii. You must understand. So ultimately again this is also a function of what? Size. You must understand. Now what are the various applications of what? Ionization potential. Let us discuss one by one its applications. But before I go there, here is what I'm telling you. It depends on what? Ionization potential basically is a function of size, and it's inversely related to size. Greater the size, lesser is ionization potentials, and alkali metals have the biggest sizes, so they will be having the least ionization potential. You must understand, right? And this is how the trend is. Size decreases, so ionization potential increases. In group, size increases, so ionization potential must be what? Decreasing. Let us go in for some of the applications. Watch carefully here. Watch. Watch carefully here. Look into this. Applications of ionization potentials. Applications of ionization potential. The first and foremost thing is 1. The second ionization potential is greater than the first ionization potential. And this is why. Right? That might be a question, a simple question. Second ionization potential is greater than what? The first ionization potential. If that is the case, then understand that this is M, right? And this is neutral gaseous atom. And from this, you have removed one electron, right? And you spent an energy I1. Now what happens? If you try and remove one more electron from this, M plus 2, and if you try to remove one more electron, then it is I2. And also remember, I2 will be greater than what? I1. And remember, whenever a positive charge is developed, and I can simply say the size shrinks. This is, the size shrunk. And from the size being shrunk, if you try to remove an electron, I think it would be harder for you. That's why I say I2 is greater than what? I1. You must understand this. Right? So whenever you try to remove one electron from, it's almost like, you have 10 apples, 10 persons. Each person will get what? 1 apple. And suppose if you have 1 person dead, so now you have 10 apples and 9 persons. I think each person will be eating more than 1 apple because 1 fellow is dead. And assuming that 1 more fellow is dead, then 8 persons will be having 10 apples. I think you will have greater percentage of the apple which is eating more than 1. So the size, when you remove one electron from it, the size goes on shrinking because the number of electrons go on decreasing, whereas the nuclear force of attraction goes on increasing. Thereby the outermost shell is pulled inwards. It becomes difficult for you to remove what? The electrons from the shrunk size. So I can simply say further I can simply say that ionization potential of, I would like to get through an explanation rather. Take an example for this. If you take aluminium, if you try to extricate 1 electron from this, and this is I1, you need to spend some energy. You have a unit positive charge. And then if you try and get 1 more electron from this, right, this is E2. And if you try to extricate 1 more electron from this, it is I3. And remember, I3 is greater than I2, which is greater than what? I1. You must understand. You must understand this. Right? So, this third ionization potential greater than the second, greater than the first. So, as the size is shrinking, the ionization potential also is increasing and it would be difficult for you to remove electrons.